record now. We do have a test scheduled for lab next time, so you guys meet for lab on Wednesday. That's going to be a test on chapters 17 and 18. And of course, you're allowed to use equation sheet. You just have to make your own. And any equations in chapter 17 or 18 that when you look at them to the right-hand side or to the left-hand side, like near the margin, there's a little parenthesis and it'll say 18-2, close parenthesis. Anything that has that is a equation you're allowed to put on your equation sheet. So those are allowed. You should have your own scientific calculator. Do not expect to use your phone for that. You can use whatever computer you might have, but what I'm going to do is tonight after class, I'm going to put up a practice test one. There's already one practice test one that you've already been hopefully taking. There's going to be another one that has a lockdown browser on it. You need to take that exactly one time before the test, or I'm going to take 2 points off your test. So make sure you get that taken. And the main reason for that is to make sure that whatever computer you're planning on using that day, if it happens to be one in the lab, then that's fine, but you still need to take it just so it's even across the boards. But if you're bringing your own computer, like a lot of students do, then you need to make sure you've got a computer that one can access the TCC Wi-Fi, two can access TCC's Canvas, three can actually take a TCC Canvas practice test or test. If it can take a practice test, it can take a test. And four, that it can run respond to lockdown browser. So all of that's part of you prepping for the test. And that's why I say I'm just going to take 2 points off for anybody that doesn't do it. So yeah, during lab time, you're going to have test one, which covers chapter 17 and 18. You're not allowed to search the web or anything like it's an online test, but it's going to be on the computer so that you can get your score immediately. It'll be a multiple choice test. You'll get your score immediately. Sometimes I'll have one or two problems that says, all right, take a photograph of your work and email that to me or something like that within 15 minutes of that sort of thing. I usually don't do that on the regular test, but there's always a chance. So just be prepared. I'll let your lab instructor, Mr. Mitchell, know if that's the case. So any questions on that?
Professor Younger,
Yes.
I have a question. Just is there a time limit for the test?
Yeah, I normally give you
It's
an
like an
hour and
hour,
15
2
minutes.
hour.
Yeah, normally 75 minutes, an hour and 15.
Okay.
But I make the tests so they're really supposed to last probably
So,
about 50 minutes, 50 minutes. So you should have plenty of time. And that means you get out a little early for lab.
okay. How many questions usually got on the test? Like 6, 7, just
I
like
usually
practice test?
have like 2 to 4 conceptual questions at the very beginning, and then 4 to 6 problems, like 2 to 3 for each chapter. And
Okay,
someone said, how do we
gotcha.
take it before we use the computers at lab? The thing is, because I have to make it so for someone, I have to make it so for everyone. So if you're not bringing your own computer to the lab, you're just taking it to make sure you know how to use lockdown browser. So whatever computer you're looking at me with right now, you use that one. So this computer will be fine.
Okay, thank you.
No problem. If you look on the left-hand side of your Canvas page, you'll see right below the Zoom link is lockdown browser. That's where you get that information. Oh, problem 8, chapter 18 problems already loaded. Isn't that nice? So yeah, just for the record, Elron, I'm looking now at chapter 18, attempt 1. Let me share the screen real quick for you guys. So what we have here is a histogram, and it's a graph of percentages on the vertical scale versus a range of velocities on the horizontal scale. You see the first number is 0 to 200. So the midpoint of that is 100. And notice that it goes up to halfway between 4 and 8. So halfway between 4 and 8 obviously is 6. So I'd write 0.06 times 100 meters per second. Plus the second one, the midline is about 300. And the percentage is obviously 34%. So I'd say 0.34 times 300 plus the midline here is 500. So I'm going to say 500 times 0.36 plus 700 times, in this case, it looks like 0.17, 0.17, in other words, times 700. And then for this next to the last one, looks like 900 times this looks like 0.05, 0.05. And then finally, 1,000 to 1,200 is 1,100 to be the midline. So 1,100 times 0.02. If you add those percentages together, you'll see that you actually get 1. So you really don't have to divide by it. But anyways, you would normally take the percent times a number plus the percent times a number plus percent times a number for all of them, and then divide by the sum of the percentages. And like I said, in this case, I think I got 474 for A, and I think 578 for part B. And the difference is in part B, you're going to square the number. So instead of 100 for the first one, you're going to go 100 squared. Instead of 300 for the second one, it's going to be 300 squared, so on and so forth. Any questions on that? So I was tickled that that problem was in the homework for this chapter, specifically because it gives you another chance to see weighted averages. I'm really surprised at how many students come to my calculus-based physics class that aren't familiar with weighted averages. So this is another opportunity for you to do a weighted average. I would say look at your transcripts in SIS or look at your course load in SIS and compute your own grade point average using the weighted average. And that would be something really good for you to make sure you can do, because that's not only the way that your grade point average is calculated, it's the same way your grades are calculated in virtually every class. And I've literally had instructors that were friends, acquaintances, or whatever that were doing their grades completely wrong. And in some cases, students got, C's when they should have got an A or something terrible like that. So you definitely need to make sure you know how to calculate a weighted average. Yes. Will the exam be taken it's not for the duration of the lab time. The test will be, like I said, probably an hour and 15 minutes will be a reasonable amount of time. And that's what I'll set it at. You should show up on time for lab. The instructor of the lab might say, well, hey, you showed up late. I'm stopping the class. If your lab started at 12, say, I'm stopping the class at 1:15, period. Right. So if you come in at 12:30, that means you only get 45 minutes and that's on you. So make sure you show up on time. I doubt Mr. Mitchell will do that, but still it's their prerogative to do so. In Canvas, the syllabus is in a module called Helpful Documents and Links. So let me pull that up and now I'll share screen with you on that and see how fast the computer can go now. It does not appear that it will go very fast. So yeah, there's a thing on the side that says syllabus. I haven't gotten that to work as smoothly as I'd like it to do the things that I want it to. So I don't put my syllabus there, but you can look, hopefully you're seeing, are you seeing this page right here with the Zoom invitation at the top? Looks like you aren't sharing it. Or aren't seeing it.
Not right now.
Gotcha. Yeah, I just noticed it was doing some weird blinking thing in the corner.
If it helps, like under the helpful documents and links, there's only 4 things. There's like your YouTube channel.
I see.
YouTube videos.
Y'all can see it now. Do you see what's going on? All of these here have been unpublished, and I don't know how that happened. So that's not very helpful at all to you guys. This one you should see and this one you should have seen. As you can tell, this is a long, drawn-out process that takes more time than it should. But this and this are the official syllabus. If I make changes to it, just like you see down here, there will be a date on the end. So it'll say, it might not even include summer 2023, but somewhere after C or after 2023, it'll say 0608 23, which just means June 8th, 2023. So if I find errors in it, I will change them and put that date on the end. And then, of course, the latest date is the most accurate one. And once we get to the date where you can no longer drop, I'm not allowed to change it anymore. So that's where the syllabus is. And now I know why you didn't see it, because clearly it had been unpublished, which I don't know why it was ever that way, but I apologize. Any other questions? Thank you for asking.
Yeah, I have a homework question. That
Okay,
is
it's not too long. I'll see if I can
homework
do it now,
question
but
number 7.
Number 7 from chapter 18, you say?
Okay.
Was it from chapter 18?
Yes, number 7, part B. Yes,
Okay.
chapter 18, my bad.
Gotcha. I'm pulling that open now to see if that's the right one that you're talking about. It's going very, very fast. I'm being sarcastic. Facetious. So I'm waiting for this window to load. It's supposed to be loading. Looks like we might be getting there now, finally. Boy, that's fast. Let's do, I'm going to stop that. I'm going to stop this and see if I can try it again. In hopes that it might be faster this time. No, it looks like it's even slower. Awesome. So the problem 7 that Bohan's asking about, on my side, it shows problem 18.17, which often means if you look up problem 17 at the end of the chapter, it'll be somewhat equivalent to this. That's also why you don't get to see that number, but that might help you if you're trying to work on this. I'm still waiting for it to load. Hopefully I can help you with it if it opens up pretty soon. Otherwise, I might have to wait till the end of class. Man, it's not going fast. Elron asked about what the 2 points off was for. So your job is to make sure before you take your test on Wednesday that you take a lockdown browser version of practice test 1 at least one time. Now, you don't even have to spend any time trying to answer the questions correctly. That's not what matters. What matters is just opening it up, seeing that it works. Ideally, it's for people that are using their own computers to run lockdown browser, but it's also for just people in general in case they haven't used lockdown browser ever before, so they can see what that's like. So hopefully that'll help you. All right. Well, it looks like this is going to Bohan.
Okay.
I'll save this till afterwards. Did that help you, Hellrun?
Yeah, that's fine.
Okay. All right. Yeah, I'm gonna
I
have to
guess it'd be
kill
good.
this, Bohan. We'll come back and look at that towards the end of class. And if
Okay.
need be, we'll do something then, or I might even set up a private meeting with you or something like that, either through Zoom or whatever. But yeah, we'll check that out. I should probably go ahead and get started. We're covering chapter 19 today. Ideally, chapter 19 could be done in a day. There's a lot of stuff in chapter 19, though, so there's a good probability that it's going to go over 2 days, which would mean, since we're covering it today, if it was a single day chapter, then the homework for chapter 19 would be due by Sunday at 11:59 p.m. But if I go over 2 days, which would mean it would cover today and Wednesday, then it'll be due Tuesday at 11:59 p.m. So I'll let you know. I'm leaning towards we're probably going to take 2 days for chapter 19, and that's certainly fine. But it's mainly just because it takes so much time. So I want to start off by saying in chapter 19, which is called Heat and the First Law of Thermodynamics, I'm going to tell you that at the time of James Prescott Joule, which might have been pronounced Joule because I know some people from Great Britain who tell me there's a beer called Joules. Joules, and that beer is actually from the same family as James Prescott Joule. And in fact, that was part of the way that that family became somewhat wealthy, is they brewed beer, and they actually made cannons and all sorts of stuff. So they were doing upper echelon, avant-garde sort of physics. And one of the things they did was something that was a really big deal. You and I, at least like right after you cover chemistry in high school, or maybe even a single physics class in high school, you probably thought 1 calorie equals 4.186 joules was a conversion factor, and it is. But at the time, the view of science was quite different. Specifically, there was heat, which they pictured as like a fluid contained by an object. So if you were talking about a cannon, for instance, made of iron, you'd say that iron contains a certain amount of caloric, which would be that liquid that we were talking about, and hence we have the word calorie. But they pictured it as a fluid, and they treated it as a fluid. And of course, it was measured in units of calories. The modern interpretation of heat is just the process by which energy is exchanged between two objects. Specifically, like if you put a hot object up, let's say this is hot, up against a cold object, let's say this is cold, then this hot object, which has a higher temperature, because we learned that the higher temperature means a higher kinetic energy, the atoms in this hotter object, atoms or molecules, will have a higher kinetic energy than the ones in this one. So the collisions between these molecules or atoms and these is going to result in these getting slightly higher kinetic energies. And one by one, various atoms and molecules will gain that extra kinetic energy till eventually the net average kinetic energy goes up for the colder object. So the colder object will actually start to warm up. And that heat will continue to flow, which, as I said, is just merely atoms and molecules from the hotter object ramming into atoms and molecules of the colder object. It'll keep doing that until basically the kinetic energy of all the atoms and molecules in this one and this one are the same. That is sort of a conservation of energy, which would be basically the equivalent of first law of thermodynamics. But it also tells us what heat is. Heat is a transfer of energy from one thing to another, usually by conduction. That's what we just did, because these two things were touching. Or convection, which would be, for instance, when you're boiling a pot of water, the pot at the very bottom gets very hot, and that causes a little wafer of water directly above that particular spot on the bottom of the pot to get hotter. And since it gets hotter, it expands. And since it expands, it becomes less dense. and that less dense water will then float up. And as it ascends, it actually cools down a little bit and delivers its energy along the way. It can deliver its energy, for instance, to the air above or whatever. But the main thing is with convection, there's a intermediate medium that the heat goes through. So the heat went from the metal to the water to something else. That's convection. And then the third way is radiation. And those are the three mechanisms by which heat can transfer from one object to another. And the second law of thermodynamics, one version of it, is that heat flows spontaneously from a warm body to a cold body. So that's the heat, that's caloric. That is something that they thought was very different, for instance, from mechanical energy. So, for instance, when we learned about potential energy and kinetic energy and nuclear energy and solar energy and all that stuff, we use joules generally. And yeah, there was a conversion factor between joules and calories, but really, we didn't use calories too much in that because it was just unheard of. And at the time of Joule doing this, basically those two types of energy were thought to be entirely different things, and the things measured in joules were not thought to be in any way equivalent to the energy in calories. So Joule actually composed or devised an experiment to do to see if there was an equivalent, and it's called the mechanical equivalent of heat. So let me go ahead and share my screen with you guys. Basically, all he did was he set up basically like a shaft that had propeller blades on it. And around that shaft was wrapped a string, and then the string went over a pulley and then down to a hanging weight. And of course, if you got a hanging weight, that means you also have the ability to allow that weight to drop, and you could take that kinetic energy, or excuse me, take that potential energy that it had from being at some height. As that potential energy drops, the energy must be going somewhere. It's actually going to heating up the liquid, and that's what he was shooting for, is to see if he could get something like that. So let's see what I'm doing here. Oh, here I am. I'm trying to put the screen up and got sidetracked because I was talking at the same time. Hopefully this will work now. Wait for it. Wait, it's very exciting, I promise. Come on. Ah, there it is. Okay. So you can imagine the experiment as being something like this. So he had sort of a calorimeter, which is just a device used to try to measure the energy changes within it. And it does so by basically insulating that system from the exterior or the outside. So we would have it filled with water, if you will. And down inside was this little shaft with propeller blades, say, and I'm drawing a simpler version of propeller blades than what your book did. Your book's actually a little more precise about what the propeller blades look like. But you can imagine if you had a coil of string wrapped around this, and then it went over a pulley, and then from that hung a weight M. If you allowed this weight to fall a distance h, then the potential energy was U equals mgh. And if you also had a little thermometer inside the fluid, you could measure how much the fluid changed temperature. And of course, the heat for that is given by Q is equal to mc delta T, where C is the specific heat. And for water, the specific heat, and that's supposed to be a lowercase c, by the way, is 1.00 calories per gram Celsius degree. And what that's supposed to be is the amount of heat required to change the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. That amount of heat is called 1 calorie. And that's where we get the idea of the calorie. Okay. A BTU, the British thermal unit, actually turns out to be essentially the same thing, except that's the amount of heat used to raise a whole pound of water 1 degree Celsius. So it has equivalent thing. But what Joule did when he did this experiment was he was able to figure out what the MGH was, and that would give him an energy in joules. And then he was able to figure out what the MC delta T was, which was able to give him the amount of heat that was required to change the temperature of the water. And what he discovered was that 1 calorie was equal to 4.186 joules. And again, I can't stress to you enough that this is not just a conversion factor. This is like a complete, new paradigm for science, because now all of a sudden they realize these two, what they thought were very different forms of energy, are in fact just two sides of the same coin. The calorie and the joule are essentially the same. Of course, you also have 1 kilocalorie, which is sometimes just written, oops, I shouldn't do that. It's sometimes just written like this: 1 capital CAL is equal to 4.186 kilojoules. Okay, so that's true as well. This is called the dietetic or dietary calorie. So when, for instance, I tell you that the 7-Eleven walnut brownie has 430 calories, what I mean is kilocalories. That means 430 times 10 to the third lowercase CAL. Okay. Now, if you take the time to look at, for instance, a label for the walnut brownie that they sell at 7-Eleven, you'll see it has like 16 grams of fat, 9 grams of protein, certain number of grams of carbohydrates. Well, it turns out that carbohydrates are worth about 4 calories per gram, and protein's worth about 4 calories per gram, but fat is actually worth more like 9 calories per gram. And that's the whole basis for like the Atkins diet and the carnivore diet and the N of 1 or N of greater than 1 diet that Dr. Sean Baker has talked about on Joe Rogan and stuff like that. So there is some sense to it. If you actually restrict your calories, you will lose weight. There's no ifs, ands, or buts about it. If you restrict the calorie intake and leave the calorie burns the same, or even increase the calorie the calories that you burn, then you will definitely lose weight. So something like the Atkins diet or the keto diet or something like that is generally just your opportunity to restrict your calorie intake by taking, for instance, something that's laden in fat, which has a buttload of calories per gram. And since you're getting 2.5 times as much bang per gram, you can eat a lot less of it and still be sustained by the same amount of energy. Okay. All right. So we now have that conversion. That is the mechanical equivalent of heat. So again, this is a very big deal. It's something that really matters. And it is also a conversion factor. Okay. Now, with that in mind, we can address a problem. Let's think, for instance, if you eat a 7-Eleven brownie, and then feel bad about cheating on your diet, you could that was, don't know why that E was there. You could decide to get on a stair climber to burn those calories. How high would you need to climb? So this is example 1. Okay, so what we're doing is we're imagining that basically you as a human can increase your potential energy by putting out or expending a certain number of calories. And what you want is to expel or expend 430 dietary calories. So they're asking, if that's the case, well, how high would you have to go? So the solution is E is equal to 430 calories, which is 430 times 10 to the third lowercase calories, which, by the way, of course, 1 calorie equals 4.186 joules. So that's what we're really shooting at here. So if I do this, I'll say 430 e to the 3 times 4.186, and I get 1.79. Actually, I should just say 1.80. So 1.800 times 10 to the 1, 2, 3, 4, 5, 6 joules is the amount of energy I should expend. So I could call that E, or I could just call that W as work to be done. And I'll clarify that a little bit in a little bit. So what we're going to say is if W is equal to mgh, then H is equal to W over mg. Well, W is 1.800 times 10 to the 6 joules. Let's talk about a typical person, obviously not your teacher. So a typical person, for instance, might have a mass of 50 kilograms. 50 kilograms would be about a 110-pound person. So I haven't seen you guys in person, but I know that's way smaller than me. But anyways, we're going to go with that. So that's just an assumption, 50.0 kilograms for the mass. And as I said, that's about 110 pounds times 9.80 meters per second every second. And that should give me ultimately the height that I have to climb. So I'm going to take that 1.8 times 10 to the 6, and I'm going to divide it by parentheses. Make sure you put parentheses in there because your calculator knows your order of operations really well. So it's going to divide by the first number and then multiply by the second one if you don't put it in parentheses. So I'll say divided by parentheses 50 times 9.8, close parentheses, and that gives me 3,673 meters. That's clearly at least 1 extra sig fig. Now, here's the deal with that, though. That's assuming that your body is really 100% efficient. Your body is not 100% efficient. In fact, nothing is 100% efficient. In fact, the human body is around 20% efficient. So really, you only have to go about 20% as high as that to burn the calories. So H corrected for efficiency is equal to 0.20, and I'll put approximately, times 3673 meters. And this is a much more reasonable thing. I'll get about 735 or 734.7 meters. So that's a lot more reasonable. Notice 3,673 meters is really on the order of a couple miles. That's a little unreasonable. Whereas 734, that's on the order of a half mile, just a little under a half mile. So that's a lot more reasonable. Any questions on that? All right. So that's our typical scenario. That's our first sort of example of what to do. Now, as I told you, this chapter 19 covers a lot of different things. So one of the things it covers is first law of thermodynamics, and the first law of thermodynamics is about the internal energy of a system. And that system could be a gas, it could be a certain quantity of gas, it could be actually some kind of canister or vat or whatever filled with several gases. It might be a canister or vat that has water in the bottom and then liquid water and then gas above it. All sorts of stuff could happen. It could be the actual vat itself, including whatever's in it. So there's a lot of different ways to define it. But in terms of internal energy, when we're talking about that, what we really mean is the internal energy is supposed to be essentially the sum of the kinetic energies of all the molecules or atoms in the substance. So the sum total of all the energy of all the molecules in an object is called the internal energy. Now, that's the sum total of all the different energies. So there's actually like potential energy because two atoms are near each other. There's kinetic energy because an atom's moving to the left. There's kinetic energy because an atom's moving up or down. And there's kinetic energy because an atom's moving in or out. Each of those, of course, is a different dimension. And each of them is a different bin of energy, if you will. So, for instance, if it's a monatomic gas, that means it's a gas that's made of a single type of atom and a single one of those, then it's basically an infinitesimal ball that can move in, out, that's one direction. It can move left, right, that's another perpendicular direction, or it can move up, down, that's the third perpendicular direction for 3 dimensions. So there's 3 bins of energy, and the equipartition theorem says that each of those bins will have exactly the same amount of energy, right? So that's just if it's a monatomic ideal gas. And again, ideal gas meaning that the atoms aren't interacting with each other. In reality, the atoms do interact with each other. There's going to be a electric attraction between adjacent atoms. That's a different amount of energy. There's going to be potential energy associated with the nucleus being built. That's a nuclear energy. All those different things could come into play. But let's start off with the simplest case, which is really the internal energy of an ideal monatomic gas. So the internal energy of an ideal monatomic gas is just the sum of the kinetic energies of the ideal monatomic gas. So when I say what is the internal energy of an ideal monatomic gas, what I do is I'll say E internal. And yes, if you've had chemistry, you might recognize internal energy as something they usually call U. In our case, we're actually going to call it E internal to keep from confusing it with the mechanical potential energy. So E internal in this case is going to be N, the number of atoms or molecules, in this case it's atoms, times 1/2 mv squared bar. But we also know that K bar, which equals 1/2 mv squared bar, is also equal to 3/2 kT, like that. So we can say that E internal is actually equal to 3/2 N times the Boltzmann constant times T. So that's what the internal energy is. Of course, you could also realize that K is equal to R over Avogadro's number, so that you could then say E internal is equal to 3/2 nRT. So that too is a reasonable and correct estimation of the internal energy. So again, you got to remember this is an ideal monatomic gas. So not O2 or N2, but maybe helium or lithium, something like that. In other words, if I had He2, or which I can't, or if I had Li2, which I could, but it's not likely. I don't think it's likely. Actually, I could be wrong on that one. But anyways, that would not be a monatomic gas because it literally has 2 atoms in it. And when you have 2 atoms, what you have is like this and this. So you've got a kinetic energy for in and out the center of mass. You've got a kinetic energy for left, right, the center of mass. And you've got a kinetic energy for up, down, the center of mass. But you also have a kinetic energy associated with this guy moving back and forth and this guy moving back and forth, which can either be looked at as 1/2 mv squared or 1/2 kx squared. Okay, so in other words, if I wanted to deal with something like O2 or N2, then I'd have to take into account not only these 3 center of mass kinetic energies, but also this 1/2 kx squared. And then I'd also have to deal with maybe this whole thing rotating about an axis like that, and that would be 1/2 I omega squared. So we get more quote unquote degrees of freedom about which this thing can move. And the equipotential theorem says that no one of them is more important than the others. So they are all, since there are such a huge number of molecules or atoms, they're all going to have the exact same amount of energy in each bin. So that was just O2 and N2. You can imagine it gets way more complicated if you start talking about H2O, which looks more like this, because then you get, oscillations back and forth here, oscillations back and forth here. You might get rotations. You might get a rotation this way. So there's a lot more degrees of freedom. And in fact, those extra degrees of freedom are exactly why water is a good insulator. because every time you put in, say, 8 calories of energy, 1 calorie will go to the center of mass of the molecule moving left and right. 1 calorie will go to moving up and down. 1 calorie will go to moving in and out. There's 3 of them. And then the other 5 bins is where the other 5 will go, but only those first 3 change the temperature. So it's got these extra 5 degrees of freedom where energy can be accepted without changing the temperature. So that makes the specific heat, which is really a measure of how bad of an insulator it is or how good of an insulator it is. The higher the specific heat, the better the insulator it is. So by having all those different degrees of freedom, you can add energy without stuff changing. Any questions on that? All right, so now we have that. And again, that's just for a monatomic gas, ideal gas. But there's also another scenario we need to talk about, and that's specific heat. So there's a quantity called specific heat. And it's given the symbol lowercase c, and it's specific, meaning it's per unit mass. So when you see these lowercase letters, that's often because they're per unit mass. That's why I tend to draw my P in lowercase and my V in uppercase, because you can actually talk about the volume per unit mass, and that's called the specific volume, and that would be a lowercase v, which you can see is V divided by M, which is literally 1 over the density. So that's why you'll see me use capital letters for that other one. But specific heat, like I said, is defined such that Q, the amount of heat added to a system, and that's what Q means, is heat added, to whatever system you're talking about. That heat will be equal to the mass times the specific heat times the change in temperature. And of course, as we've been beating into your head, delta always means final minus initial. So this delta means T final minus T initial. And I'll put a little asterisk up there because there's a caveat, as always. We'll talk about that caveat a little later. But the main thing is there's a couple different ways you can solve calorimetry problems. One that a lot of books use is the sum of the Q's is equal to 0. If you do that, then yeah, you need to do T final minus T initial everywhere. I have found that students don't necessarily do very well with that method. I use something different. I say there's a certain number of parts of a system that are losing heat, and then there's a certain number of parts of the system that are gaining heat. And I use the ones that are losing heat, I sum them all up and put them on the left side, and the ones that are gaining heat, I sum them all up and put them on the right side. But in doing so, I need to make sure all those terms are positive. So that forces me sometimes to do T initial minus T final. So that's the caveat. But we now have a wonderful equation that tells us how matter changes temperature. When you add a heat Q to a system, the change in temperature will be given by the heat added divided by its mass and divided by its specific heat. Therefore, the larger the specific heat, the smaller the change in temperature. And the smaller the specific heat, the larger the change in temperature. So that's something we can use. Your book even has some tables on specific heats. For example, the specific heat of aluminum, which you'll probably do in lab, is 0.22 calories per gram Celsius degree, which can also be written as kilocalories per kilogram Celsius degree, or you can say it's equal to 900 joules per kilogram. I don't know why I wrote a 4 there all of a sudden, per kilogram Celsius degree. So that's another version. And you can tell the conversion factor there is essentially 4.186. Okay. Another one, say copper. The specific heat of copper turns out to be 0.093 calories per gram Celsius degree, which is the same thing in kilocalories per kilogram. Notice I'm just multiplying by 1,000 and dividing by 1,000, but that also happens to be about 390 joules per kilogram Celsius degree. As I said, water, and I'll say liquid, is 1.00 calories per gram Celsius degree, which is 4.186 joules per gram Celsius degree, are 4,186 joules per kilogram Celsius degree. That's just liquid. For ice, it's about 0.5. And for steam, it's about 0.48. And I should probably write this ice a little better because I can see that looks like he. So I'm going to say ice. Okay. And I just left it in the units of calories, that sort of thing. For reference, though, you might notice the human body has a specific heat of about 0.83, which sort of indicates that, yeah, the human body is essentially mostly water. And, sometimes you might just have a, dead body laying around in a pond and you're wanting to know how much it's going to change the temperature of the pond. I hope we never have to solve such a physics problem, but there we go. Your book also gives the specific heat of a protein, protein like you eat, and that turns out to be about 0.4 calories per gram Celsius degree as well. So, any questions on that? You might notice it is 0.4, and if you want to make that a dietary calorie, what are you going to do?
Multiply by 1,000.
Yeah, multiply by 1,000. So that's going to give you about 400 calories per gram, which obviously is a little different, but we've been using the idea of 4 calories per gram. Okay, for proteins, carbohydrates, and then for fat, of course, it's 9. Any questions on all that?
Can you keep the screen up for just like 10 more seconds?
Yes. Blow it up to this, seeing this bottom part?
Yeah. Thank you.
Okay. Now, the good news is you don't need to really memorize these, though you'll probably end up memorizing the ones for water because we're really required to give them to you. Okay, unless we explicitly were to tell you, hey, you need to memorize this one, this one, this one, and this one. We're supposed to give them to you. So when you're doing an actual test on this material or something like that, you can expect to either be given the table of the specific heats or be given the specific heats that you need. Now, with that in mind, I'll talk a little bit about calorimetry. And what calorimetry is, and you're going to do a lab on this, so that'll help you a little bit. But what calorimetry is is where you try to limit the amount of heat that comes into the system, but without you measuring it, and the amount of heat that might leave the system without you getting a measure of it. In other words, you really want to know exactly what's going on from an energy standpoint within the system. Okay. So ideally you want something that creates a adiabatic environment that you'll learn later. One of the terms that we use in addition to isovolumic, isochoric, isobaric, and all those things, there's a term called adiabatic. And that just means heat doesn't enter or leave the system. Okay. So the way we implement that in lab, as you'll see next time, is we'll take a little aluminum container that is essentially an aluminum cup, and it has a sort of a little ledge around the outside, and then it comes down like this, and essentially just an aluminum cup. But the special thing about the aluminum cup is that we can measure the weight, and it's pure aluminum, so we know exactly what its specific heat is. But since aluminum is actually a pretty good conductor, you can see the specific heat is 0.22, whereas water, which is a good insulator, has a specific heat of 1, which is nearly 5 times as big. Aluminum is actually a pretty decent little conductor, and therefore it's going to readily conduct heat away from the system and into the system. We don't necessarily want that. So the next thing you do is you take and use a little wafer of cardboard or wood or something that's just an insulator, and you use that and you make it narrow so that it really doesn't have much surface area to contact the aluminum cup, but you use it to hold the aluminum cup up inside of another container. So I'm going to put a little ring around that, and then I'm going to take and make it sit on a little ledge inside of yet another aluminum container. This aluminum container will go up like this. Let's say like that. And of course, this one's going to be an aluminum container too. But notice how it's sort of thermally isolated from the inner cup. It's not completely thermally isolated because you can see that clearly heat can leave the aluminum cup and go into that little black wafer. And that would be a bit of a problem, obviously. But because the wafer is so thin, it's not going to be much of a problem because the heat loss is directly proportional to the area of contact and inversely proportional to the distance over which it's got to travel. So putting that inside of that container, you can even put an insulated lid on it, which we have, but we never have to use because it's actually good enough this way. But by doing that, I've now allowed air that doesn't move. So right here is air, and it just sits still instead of moving. So that gets rid of convection currents as well, because for convection to occur, you'd have to have it heating up, and then the air inside of it would have to be heated up and then rise, but it can't rise because it's got sort of a lid that keeps it from rising. So that only leaves really radiation, because there's only 3 ways for heat to transfer. So heat transfer is conduction, convection, and radiation, which means electromagnetic waves traveling through space at the speed of light. Okay, so this more or less cuts out the conduction because the only part that's touching is that little thin wafer of cardboard or wood or whatever, and it only touches a itty bitty ring around the bigger outer aluminum cup. So that too is a small loss of heat due to conduction. And then convection, we stop by basically not allowing currents of air to go up and down through the space between the inner cup and the outer cup. Radiation is still a possibility, but radiation, you pretty much are going to have a hard time stopping anyways, depending on the wavelength. It only gets stopped or slowed down or deflected by things whose distance between them or whose size is comparable to the wavelength. And of course, the wavelength here that we're talking about is the infrared, which is on the order of millimeters or something like that. So that's not going to happen. But that's a calorimeter. That's one, calorimeter. And that's actually a fairly cheap calorimeter because, we have a bunch of them. But it works pretty well. We normally get, 5% of air or less when we're doing experiments used to determine the specific heat, for instance, of a substance like aluminum or copper or tin or zinc or something like that. So when we use that, what we do is, I'll say, because it's fairly efficient, means that heat lost is equal to heat gained. So as we told you, spontaneously, heat flows from a hot body to a cold body, whether it be through conduction, convection, or radiation, doesn't matter. The main thing is it goes from the hot body to the cold body. So all the things that are hotter than the other things, they're going to be losing heat. And all the things that are colder than others are going to be gaining heat. So these are cold bodies over here. That's the way I like to do it. And again, this forces each term has to be positive. And that means this side as well as that side. Okay. So delta T is not necessarily T final minus T initial. And now I'm saying not necessarily, well, sometimes it is. So let's imagine, as another example, let's say 5.00 liters of 98.0 degrees Celsius tea which should be thought of as approximately water. Now, that's not necessarily the case. I'm just saying that's the way we're going to solve it. I've seen some very, very sweet tea, and that's sort of quite a bit thicker than water and quite a bit different from a thermodynamic standpoint, but we're going to assume it's like water. So 5 liters of 98.0 degrees Celsius tea has a 2-pound negative 10.0 degrees Celsius block of ice put into it. what is the equilibrium temperature. Okay, so this one's a little different just because we're using ice. And what's going to happen when you put cold ice in a hot liquid? It's going to melt. It's going to change state. So it turns out when you actually change state, there's a whole different batch of energy that goes into it. I've talked to you about it before, but basically, as you're heating up, say, tea, or as you're cooling down tea, you're stealing energy from the individual molecules. Those individual molecules are reducing their kinetic energy by slowing down. And they're being slowed down by colliding with other molecules, and those molecules are stealing some of the kinetic energy. But as you get colder and colder and colder, it starts to reach zero. But once it reaches zero, nothing else can happen until you allow it to get enough energy where the individual molecules, which are sort of rolling all over each other in a liquid state, are all of a sudden, boom, locked down in a nice lattice. That's that latent heat. And it depends which way you're going as to whether heat's got to be added or heat's got to be taken away. So, for instance, if it's a solid, meaning like ice, then you actually have to add just a little bit more energy. And I say just a little bit, it actually could be quite a bit. You have to add a little bit more energy to it to break the bonds of the individual atoms or molecules that are in the lattice. So you basically add heat as you raise it up from negative 10 degrees Celsius to 0 degrees Celsius. Then when you get it to 0 degrees Celsius, all of it stays at 0 degrees Celsius until you melt it all. And you can't melt it all until you add what's called the heat of fusion to it. And technically, fusion is what happens when you go from liquid to solid. But we're actually going from solid to liquid, so it's just the opposite in sign. But that is the case. And in fact, there's a nice diagram in your book on water, and it shows you basically a temperature on the vertical axis versus energy added on the horizontal axis. And you'll see that basically it starts at, say, negative 20 degrees Celsius. And that slope really is the specific heat, because they're talking about like 1 kilogram of water. So it's goes up kind of quick, and then it reaches 0 degrees Celsius. And then it doesn't budge until you add 80 calories to it. That 80 calories, I think it's 80 calories, is the latent heat of fusion. So you got to add that per kilogram to make it change state. And then it goes up at a different steepness because the specific heat of liquid water is different than the specific heat of solid water. But it goes up till it gets to 0. And then it levels off again. And you don't get it changing state until you add, I think it's like 510 calories or something like that. And then that's the latent heat of vaporization. Once you've added that, then it starts to rise again with a different slope, this time the slope being the specific heat of steam, and so on and so forth. So that's the whole process. So when I put a block of ice in here, what's first going to happen is the block of ice is going to absorb as much heat as it can until the entire block of ice is brought to 0 degrees Celsius. If the tea is now 0 degrees Celsius and the ice is 0 degrees Celsius, then you're golden. If it gets less than all of the ice turned to 0 degrees Celsius, but the tea turns 0 degrees Celsius, then that's all the ice that's going to change temperature. However, it might even take more energy, in which case it's going to start to change state as well. So that's what we're working out. We're going to try to figure out the equilibrium temperature. I'm first going to just look at the ice. So let's look at the solution here. The solution, as always, is Q lost equals Q gained. Again, that's the way I do it. And I just make sure my terms are all positive. And this heat of vaporization and heat of fusion and heat of sublimation, these latent heats are exactly why I found this way to work better, because it really gets kind of confusing whether the L is going to be a positive or negative, depending on which direction you're going. This just locks down everything to have a positive sign. So I will say the loss heat will be lost from the T, and the gained heat will be gained by the ice. So I'll put that there. So first off, what we're going to do is we're going to say that 5 liters of water is, in fact, since we know the density of water is 1 kilogram per liter, that's 5.00 kilograms of water. Remember, Q is equal to MC delta T, and Q is equal to ML. So 5 kilograms of water with 4.186 joules per gram Celsius degree. That's not a convenient unit. We're going to make it 4,186 joules per kilogram. And then times, in this case, the temperature is actually going from high to low. We want this quantity to be positive. So I'm going to take the initial temperature, which is 98.0 degrees Celsius, minus T final. And that way it'll make sure it's positive. Now, this is me just checking if we can do this just by changing the temperature of the ice without actually changing its state. So I'm not taking into account the ice change in state right now. All I'm doing is taking into account MC delta T. So the heat gained in this case is for the ice, and the ice was a 2-pound block, which we'll say 2 pounds is about 4.4 kilograms. So 2 pounds of ice, and I'm really being approximate here. Or excuse me, 2 divided by 2.2. Sorry about that. That's about 0.909. The eraser, which always comes on, will not come on when I need it. Okay. 0.909 kilograms. Now, if you multiplied 0.909 kilograms times 2.2, you'd see that you do get about pounds. Now, to be honest with you, ice is a little less dense than water. That's why ice floats. But I'm just roughly saying 2 pounds is essentially 0.909 kilograms and going with it. So it's not, I'm not being very strict here. I'm just checking. So I'm going to say 0.909 kilograms. Now, the specific heat of ice we found was 0.5. So I'm going to say 0.500 calories per gram Celsius degree. But I need that to be in joules since that's what we were working for. So that's 4.186 joules per calorie. And then I also need it to be in kilograms. So 1,000 grams is equal to 1 kilogram. That's going to have to go there. And that's those 3 things right there. These 3 are just making the units of C right. Now I've got to have one more multiplication, which is the change in temperature. Now, in this case, the ice is actually going to be at a final higher temperature. So it'd be T final minus negative 10.0 degrees Celsius. Okay. So if we find out that the T final is actually something that's doable, then we can say, okay, well, the ice isn't even going to melt, but we're going to calculate that. Now that has to be, for instance, 0 degrees Celsius. So if we count this, so try 0 degrees Celsius. So the left-hand side, when I do 0 degrees Celsius, is going to become 5 times 4186 times 98, and that'll be 2.051 times 10 to the 6 joules, whereas the right hand side is going to give me 0.909 times 0.5 times 4186 times 1000 times 10. And this gives me 1.903 times 10 to the 7th joules. Okay, so if we really wanted to bring the whole block of ice to 0 degrees Celsius, we're going to have to need a buttload more energy than can be supplied by the T. So we now know clearly that's not what's going to happen. So now what we can say is, all right, well, we're going to bring the ice up to 0 degrees Celsius, or some fraction thereof, and that's not necessarily going to be enough to cool it all the way to 0. Okay, so now we can actually solve this for T final and see what happens. So I'm going to say 2.051 times 10 to the 6 joules minus 5 times 4186, 5 times 4186 is equal to minus 20,000, 2.093 times 10 to the 4th joules per Celsius degree T final is equal to, now I'm going to do the same thing. This should be about 1.903 times 10 to the 7th joules. That's just for the part without the T final. The other part is going to be 0.909 times 0.5 times 4.186 times 1000, and that should be it. That gives me 1.903 times 10 to the 3rd joules per Celsius degree T final. So this actually allows me to try to figure out exactly what TF is. If I bring the T final term from the left-hand side to the right-hand side, that's 2.093 plus 1.903. One's times 10 to the 4th and the other one's times 10 to the 9th. So 2.093 e to the 4th. I'm going to say plus 1.903 e to the 3rd. That gives me 2.283 times 10 to the 4th joules per Celsius degree T final. That's the unknown side. Now what I get is 2.051 e to the 6. Now I'm going to subtract from that minus, and here's where all the wheels fall off, 1.903 e to the 7th. And that gives me a negative. Okay. That gives me a negative 1.698 times 10 to the 1, 2, 3, 4, 5, 6, 7 joules. So you can see clearly this is only going to bring it up to a certain negative temperature. And in that case, we're actually starting to talk about the ice, the tea actually freezing. Okay. So if I divide this number by the 2.283 e to the 4th, I get, whoa, that can't be right. Yeah, that was exactly right numerically. So that's giving me like negative 743, which is clearly unreasonable and undoable. Okay. So obviously something went crazy on that. I'm trying to piece that together right now. Hold on a second. Obviously, since we've got such a big mistake, the actual getting of the notes for this isn't going to be that important or helpful. So let me stop sharing real quick and talk about what's going on. And actually at 6:55, okay, we're not doing too bad on time. So what I just calculated was the heat being lost by the T. Okay, that heat is going to heating up the ice. So we're assuming both of them are only using MC delta T, because we're not, changing state yet, but we don't know exactly what's going to happen because we don't know the magnitude. So it might have been better, to say put a small piece of ice in there and then calculate that first. But I tried to jump ahead so I could show you two things at once, and my idea went to crap, basically. So I apologize for that. But I think you can still see essentially what's going on with this in terms of what the terms are and how you choose your delta T such that the delta T is going to be final. If you're going to use Q loss equals Q gain, you need to absolutely say whatever the delta T is, it doesn't have to be T final minus T initial. It just has to be positive. So when we did that, we found that basically 5 kilograms of tea versus 0.909 kilograms of ice, it took way more heat, according to, assuming I did this all right, it took way more heat to bring the ice up to 0 degrees Celsius than it took to bring the tea down to 0 degrees Celsius. That's surprising. I didn't expect that. Maybe I might have made a calculation error when I got the 1.903 times 10 to the 7th. Not really sure because I had some computer difficulties, so I didn't get to practice my problems before I came in here, and I'd made this one up and hadn't worked it yet. So that's what went wrong with that one. Now, what we also have to do is we have to figure out, what fraction of it actually melts. What did I do wrong in this calculation? I'm thinking that there might be something wrong on that. So we're just going to have to scrap that particular problem. That's just because I screwed up. I'm sorry. That being said, we can still solve a fairly reasonable problem. So let me show you another one in hopes that this one will make a little bit more sense. So what I'm going to do is share the screen again. Does anybody have any questions on what we did there? I know the result was kind of crappy, but hopefully you understand what I was doing with the left side and the right side and why we only used MC delta T there. Yes, you can certainly take a 5-minute break. Nora, let's go ahead and give you guys a 10-minute break. That'll give me some time to see if I can figure out anything wrong with that. So it's 6:58 now. Come back at 7:08. I'm going to be here, so you can still ask me questions, but I'm also going to try to see if I can trace down what I did wrong. So everybody go ahead and take a break. I'm sorry. I will try to give y'all a break every night. I just get excited sometimes and forget. Thanks, Nora.
Thank you, Professor.
No problem. Sorry about that. So I'm looking at, okay, I got all that. All right. I got all y'all's stuff. So All right. Looks like it's about time. So I did in fact discover a mathematical error. It looked like everything else I did was okay, but there was a mathematical error. So I've tracked that down. That's good. It's pretty straightforward to see. I got a really big value for Q in changing the temperature of the ice from -10 to 0, like a factor of 10 higher than the calculation provided for changing the temperature of T at 98 degrees Celsius to 0. So that was what was bothering me even when I did it. So I just recalculated that to make sure, and sure enough, I got a completely different answer. So now what I'm going to do is go ahead and show you what calculations I did so you can see how I corrected it. And then I started another solution to make some sense out of it. I think it's more important that we get through this calorimetry type problem than it is for us to jump into the next section. So I've basically decided we are going to spend another day on chapter 19. So chapter 19's first homework assignment will be due Tuesday of next week, not Sunday of next week. Okay. So what I did right here is, if you look, it says second try with ice. I remember the initial temperature of the ice was -10. The mass of the ice, again, going on the assumption that the ice is about the same weight as water, which is completely wrong. I should really divide this by like 0.98 or something like that, or excuse me, multiply by 0.98. But we're just going to go with it and assume that's approximately what I said in the original problem. And then I decided to just use joules because I suspected there might be a problem in my conversion between joules and calories that might have led to the problem. So this time I used the actual caloric values in joules per kilogram Celsius degree. And then I did the same thing for T. And you can see that the heat required to bring ice from -10 degrees Celsius to 0 degrees Celsius is just 19,089 joules. I previously had this god awful figure of what was that? It looks like I had the right hand side was 1.9 times 10 to the 7th, so 10 million or 19 million joules. That was clearly a mistake. So I don't know where my error was, but I clearly had a bad error, so that was not promising. That being said, now that I can use this, I'm just going to say, okay, clearly I made some mistakes. The QT, in other words, the heat required to bring the T down to 0 is way, way bigger than the heat required to bring the ice up to 0. So I'm going to try it again. This time I realized that the ice is going to have a final temperature of 0. And then it's going to start changing states, but the T is going to have to stop at T final, which we don't know yet. Okay, so I said 5 kilograms times 4186 joules per kilogram Celsius degree times 98 minus T final. Notice that's again in the order of subtraction that gives us a positive delta T. Now that change in heat is going to be equal to the mass of the ice, which is 0.909 kilograms, times the specific heat of the ice, which is 2100 joules per kilogram Celsius degree, times 0 minus -10, which is +10. So I get those figures, then I solve for T final, and I see, in fact, bringing the ice up to a temperature of 0 degrees Celsius literally only brings the T from 98 to 97.09. I'm surprised. So there might be a mathematical or arithmetic error in that again, because I really didn't expect it to be that small of a quantity, but it is more than 5 times the mass of the ice. So, and in fact, the specific heat of ice is less than half, or about half of what the specific heat of water is, which is what we pretended T was. So maybe that's reasonable. I'm not sure. Now I've gotten that the T is up to 90 or down to 97 degrees Celsius. What I want to do now is use that T to change the state of the ice. So now I'm going to say 5 kilograms of ice, or excuse me, of T, times 4,186 joules per kilogram Celsius degree, times, now I'm going to say 97 point, well, actually the final temperature is going to be lower. So yeah, 97.09 degrees Celsius minus T final is equal to, now I'm going to go 0.909 kilograms of ice. And I'm going to pull up the heat of fusion for ice, or for water more specifically, which is obviously going to become ice. So I'm going to pull up that from the table in the book. That's in the section 19.5, which is latent heat section. So for water, the heat of fusion is 333 kilojoules per kilogram. So 333 kilojoules per kilogram. And now, of course, the left-hand side is giving me joules, so I got to say 1 kilojoule on the bottom is equal to 1,000 joules on the top. That'll convert it to that. And that's the whole thing. That's all the heat that's required to do this here. So if I do 5 times 4186 times 97.09, that gives me 2.032 times 10 to the 1, 2, 3, 4, 5, 6 joules minus 5 times 4186. Plus, that's just the part with the TF. So that's going to be 2.093 times 10 to the 4th. And that's joules per Celsius degree times T final. That's all equal to 0.909 times 333 e to the 3. Because e to the 3 is the same thing as multiplying by 1,000. So I get 3.027 times 10 to the 1, 2, 3, 4, 5 joules. So I can now say that after melting the ice, T final should be, I'm going to take the 203.7. That's actually the whole number. Minus 302,697. Again, that's the whole number I calculated. And now I'm going to divide that by the 20930. And that gives me 82.63 degrees Celsius. So bringing all the ice to become actually water is obviously going to water down the T, but I've now gotten the T down to 82 degrees Celsius, but the ice that's been melted is still at 0 degrees Celsius. So now I need to see what is the final temperature. So that's going to bring the last part. So 82.63 is what we got now. So now I'm going to bring the melted ice to an equilibrium temperature. Supposed to be an M there. With, I don't know what happened there, with the cooled T. So how do I do that? Well, I'm going to say 5.00 kilograms times 4,186 joules per kilogram Celsius degree times 82.63 degrees Celsius minus T final being smaller, so I had to have that second, is equal to 0.909 kilograms. Now remember, the mass doesn't change. That's why I keep writing 0.909 for the ice. Now the ice is officially no longer ice, so that has a 4186 joules per kilogram Celsius degree. And its temperature is initially 0, so now it's going to be T final minus 0 degrees Celsius. Okay, so that times the -0 is just going to give us 0. But when I do 5 times 4186 times 82.63, I get 1.729 times 10 to the 1, 2, 3, 4, 5, 6 joules minus 5 times 4186. That's the 20,930, I believe. Yes, is 2.093 times 10 to the 4th T final. Now, actually, those units, let me go ahead and correct that. Those units turn out to be joules per Celsius degree times T final. This one over here is going to be 0.909 times 4186 is 3.805 times 10 to the 3 joules per Celsius degree T final. Okay, so I'm going to get 1.729 times 10 to the 6 joules is equal to, now when I add that to the other side, the 3.805 times 10 to the 3rd plus 20930 is going to give me 2.474 times 10 to the 4th joules per Celsius degree T final. So T final is going to be 1729445.9. I'm using the whole digits there. All that's going to be divided by 24735.074, again using all the digits, and this gives me 69.92 degrees Celsius is the final temperature. Now that's sort of the ugliest of the ugly, and not to mention the fact that I made a boo-boo in the beginning that made it even uglier. So that's suboptimal, obviously. But anyways, does everybody understand what we did there? I had to break it up because the ice might have been so massive that it would have brought all the T down to 0 degrees Celsius, and then we'd have what most of us call true iced tea. True iced tea is iced tea that's so cold that it's literally 0 degrees Celsius. It's just on the cusp of freezing. That's sort of the holy grail of iced tea, at least on a hot day. So we found out that was not nearly enough ice, even though in reality I used a much heavier 9.909 kilograms than was warranted for ice, because obviously the density of ice is less than the density of water. So that wasn't enough. So first what I did was I calculated, all right, let's bring the entire chunk of ice up to 0 degrees Celsius. How much is that going to require the T temperature to change? Therefore, I had only one T final, and that was the T final of the T, because the T final for the ice was just 0 degrees Celsius. that turned out to lower it just less than 1 degree Celsius by melting all the ice, or excuse me, by bringing all the ice to 0. Then I said, okay, let's try melting all the ice. In fact, I might have enough ice that melting it alone would bring the T to 0. We found that was not the case. In fact, it brought the T temperature to 82.63 to melt all the ice. So I found that temperature. And then finally I said, now I have 0.909 kilograms of what was ice, but it's now just water at 0 degrees Celsius, combined with 5 kilograms of water at 82.63. Obviously, the T, which is hotter, is losing heat, and the ice, which is colder, but even though it's now water, is actually gaining heat. So I set those two equal to each other with their T final in it, and that gave me 69.92. So in principle, if we did this, if we added 5 liters of 98 degrees Celsius T to about 2 pounds of ice at negative 10 degrees Celsius, we'd expect it to all reach equilibrium around 70 degrees Celsius, which is still way too hot to drink. You still have to water it down, that sort of thing. And also it shows you, since all of that ice melted, you clearly want to make sure you make the tea extra strong so that when it's watered down, it's still good. Any questions on that? All right, so that was a big type of problem. That's called calorimetry. And in fact, your book talks about a bomb calorimeter, which is what you use if you want to figure out the number of calories. For instance, in my 7-Eleven walnut brownie. In fact, one of my best friends from high school owns a hot sauce shop in Virginia Beach and makes his own hot sauces called Speedy 44, Speedy 45, Speedy 46, and various other things. Really good hot sauce. Highly recommend it. But anyways, my friend Jimmy went to make this product. And of course, one of the things you have to do when you sell a product is you have to make a nutritional label. So he sent his hot sauce off to Virginia Tech, and they do that as a service. They actually have a bomb calorimeter, and they would take the actual hot sauce and put it in the bomb calorimeter, and that actually causes the food to burn and calculates how much energy comes from it, and that is what you get, basically the number of calories that come out of a particular thing. For instance, a 7-Eleven walnut brownie. So that's something they do, and that's what bomb calorimeters are for. That's one of the things your book talks about. The other thing that I wanted to show you in chapter 19 before I go on, we still have about 24 minutes, is I wanted to talk to you about that actual graph of water being raised to specific temperatures. I think that's in the latent heat section. Yeah, it is. Okay. So let me give you an idea what that graph is. This is figure 19.5 in your book. So I'll say see figure 19-5 in your text. Now, what I'm going to show you is a graph of, now in this case, the graph is temperature on the vertical axis in degrees Celsius and heat on the horizontal axis in kilocalories. So this is actually just plain Q in kcals. And this is all for 1.0 kilogram of ice at negative 40 degrees Celsius. Okay. So what's going to happen is the specific heat of ice is such that it's 0.5 calories per gram, But if you go back to table of 19.5, 0.5 times 4,186 is 2,050, 90, 93. So that would actually be the slope of it. And you can say this little quantity right here is going to be negative 40. And then I'll say negative 20. And then 0. And then 20. And 40. And 60. 80. And 100, like that. Okay. So it's going to go from 0 to, or excuse me, from negative 40 to 0. And after a short amount of heat. Now, what's that heat? Well, if you took the specific heat of ice and multiplied it by 1 kilogram, because that's how much mass it is, what you'd find is the answer is about 20. So this is going to be 20 kcals. And then the ice is going to stay nice and cool. I'm going to indicate that there's a gap in the thing here, so that this right here, this temperature is, or excuse me, this calories is 100, like that. So this is going to be perfectly flat from kilocalories equals 20 to kilocalories equals 100. So what that amount of heat is right here is the latent heat of fusion, which equals 80 kilocalories per kilogram. Okay, because 100 minus 20 is 80. Now we're going to go from 100 to, let's say, 120, 140, 160, 180, 200, like that. And that's going to bring our water temperature up to 100 degrees Celsius. Okay. Notice the slope there is quite a bit different. That's because the slope is related to the specific heat. Remember, we're solving for delta T. So delta T is actually equal to Q over MC. So it's really inversely proportional to the specific heat. So that's why the slope looks a little smaller here than it does on the water. And actually, I just realized I missed the mark. So let's erase that. I did not mean to erase all that. In fact, I'll put it all back. And now I'm going to just do an eraser mark. You go away now. Okay. I want to do this. Okay, so that slope is in fact 1 over 1 kilogram, still in the bottom specific heat. And now here's the big kicker. If I want to now convert this water to steam, then I have to add a butt ton of kilocalories. And it turns out I will again make a jump in the axis and say this figure right here, actually, this figure right here is going to be 740 kilocalories. And my graph is going to, dang it, my graph is going to look like this. So there. And then it'll rapidly go up again for the rest of it. Now you can see 740 minus 200 is 540. So this right here, from here to here, is the heat of vaporization, LV, and it's equal to 540 kilocalories per kilogram. Okay. So that's what I was talking about, changing state. And that's also, you know, why we boil water when we're cooking sometimes. Boiling water allows you to get a heat bath that stays at a constant 212 degrees Fahrenheit or 100 degrees Celsius, assuming you're at 1 atmosphere pressure. If the pressure is a little low, maybe there's a thunderstorm coming, maybe it's going to be 213 degrees Fahrenheit or 214 degrees Fahrenheit or 100.5 degrees Celsius. The main thing is it keeps a constant temperature. So if you have a big chunk of meat, slowly but surely that heat can penetrate from the outer edge to the inside and make the whole thing reach some critical temperature, which for like pork and chicken, it might be like 165. And for beef, it can be quite a bit lower. Well, safely speaking, it can usually be quite a bit lower. Anybody have any questions on how that process panned out?
Yeah, I just kind of wonder how do we know that's 100 from like I get when you get a 20 how do you get a 20, but I kind of don't know
Right.
how do you locate 100 on the axis.
Okay, so in this one, I'm actually just stealing the diagram from the book. But if you choose to look at it, you realize it's 1 kilogram, and then you can look at table 19.1 that has the specific heat of ice, which I think was that 2100 specific? Yeah. 2100 was a specific heat. So if you multiply 1 kilogram times 2100 times 80, which is really the temperature change from 20 to 100, I think you'll figure out that's exactly the 80 kilocalories that you need. So 1 kilogram times 2100 times 80 gives me basically 1.68 times 10 to the 5th. And then of course you can convert that back. That's what it's supposed to do. Now, excuse me, that's the wrong part. That's the 20 to 100 I got from table 19.2. Let me write that. So latent heat are in table 19-2. So that's where those values come from. So the 80 kilocalories per kilogram you can see is listed actually on table 19.2, which we don't have page numbers because it's electronic, but basically you can see it's actually 79.7. So LF is actually 79.7 kilocalories per kilogram. And if you actually look at it for water with regards to heat of vaporization, that turns out to be L vaporization equals 539 kilocalories per kilogram.
Oh, okay. I see the table.
Okay. I thought that's what you were asking. Initially, I thought you were asking how you knew how much heat it took to change, but then as I started answering it, I realized that I thought you were saying the other thing. So I'm glad you clarified that.
Okay.
Good deal. Anybody else have any questions? All right, so that's the process by which matter changes state. Of course, anybody know anything about carbon dioxide? Does it do something funny that y'all recall?
Isn't there something where it like jumps states?
Yes, it's
The-
dry ice. If you've
yeah,
ever heard of dry ice, yeah, that's CO2. So, or you can watch the movie Real Genius, which I think might have been Val Kilmer's big screen debut. So I definitely recommend that cheesy 1980s movie. But anyways, yeah, CO2 switches straight from solid to a gaseous state. That's called sublimation. So in fact, there's also a latent heat of sublimation that you could look up for instance, for CO2. Just like everything, though, when you're skipping states or even when you're changing states, it's not really just the temperature that matters, it's the pressure as well. So there's often parameters like that that are relevant. Similarly, there's often different specific heats you have to use for different temperature spans. That's something to keep in mind when you're doing actual work as opposed to just problems to learn how to do physics. When you're doing actual physical problems, you really want to get a very pristinely correct answer. So if you're going from a temperature of, say, 0 degrees Celsius all the way up to 100 degrees Celsius, you want to look up specific heat for that particular substance at as many temperatures as you can between 0 and 100 degrees Celsius. And then whatever temperature they're at, say they're at, let's say they're at 20, 40, 60, and 80, you want to use the 21 from maybe 0 to halfway from 20 to 40. And then you want to use the 41 from 30 to halfway to 60, which is 50, and so on and so forth. So you always want to use the best data you possibly have, and that's the way you go about doing it, is just find out what values you have for a given temperature or a given pressure. Any questions on that? Your book takes the time to say, it gives you this problem solving sort of essay, and it says calorimetry, and it tells you how to do these problems, and it actually then walks you through example 19.8, which is determining the latent heat of mercury. So those are really good examples. I highly recommend you look at those. And of course, the rule is really you're supposed to be going through, reading your chapter, read section 19.1, make sure you can do the example, try even closing the book, and then see if you can at least work out the example in your head, and then look back and see if you did it right. If you did, then it's time to move on to section 19.2 and repeat and repeat and repeat. When you're all done with making sense of all those examples and going back and rereading if you can't do those examples, then you might want to consider, as I was telling a student today, what I used to do was I would make sure I can work through all those examples myself. And that might require me to read section 19.3 3 times, but section 19.1 and 19.2 I could get by in one. Once I was done getting through all those examples, I'd then go to the end of the chapter and look at the odd problems. And if I really found the examples easy, maybe I'd just take one of the higher odd problems from the section that the examples were easy and see if I could solve that. If I could, I'd feel pretty confident with my knowledge of those sections. If I had a hard time with every example, then I'd probably start with one of the first odd questions in that section. Because notice in the end of the chapter, the homework problems in the end of the chapter are listed per section. Like there's a homework section for 19.1 and 19.2. So you start at number 1 and number 3 if you had a hard time with the examples in section 1 and section 2. If you didn't, if you blew through them and they all made perfect sense, maybe you start with number 17 because it only goes up to, say, 25. So that would be a good choice. And then once you're finished reading the entire chapter, that's a good time to go back and attempt to do your homework and or practice tests. And the homework is really the homework as well as the examples, as well as the stuff at the end of the chapter that I was suggesting you try. All of that's meant to further teach you how to apply physics to real problems. That's not necessarily, well, it is to prepare you for the test, but it's not necessarily the whole purpose of it. The test is often quite a bit different because the test is trying to make sure you understand all the topics, but not necessarily in the extreme depth that all those examples and chapter problems and homework problems did. So at that point, you want to start doing the homework, or excuse me, the practice tests, because those are and have been for about 10 years now exactly the problems I use on the test. I reserve the right to change 20% of the points to entirely new problems, but I haven't needed to do that in 10 years, and still students are not necessarily blowing the doors off. So I don't mind keeping that. So the more of those practice problems you do, the better place you are to take a test. Any questions on that? All right. So now that I give you that talk, and I've told everybody, I'm going to re-announce it again. There will be a practice test for test 1 that's going to have the word lockdown browser or respondus or something in the title. You need to take that once. You don't need to worry about the grade. You can just guess your answers. They're all going to be multiple choice anyways. What you get on it grade-wise doesn't matter. It's all about using your computer to see how a respondus lockdown browser works, what it does, what it doesn't do, all that kind of stuff. So I need everyone to do that. And if you don't do that before the test, I'm going to take 2 points off your test grade. Obviously, I don't want to take any points off your test grade. That's just dumb. It's just me trying to encourage you to make sure you do it so we don't have this problem when you come into lab and try to take your test. You know, Mr. Mitchell will have to help you get set up. That's not what Mr. Mitchell's time is best used as. So you guys make sure you do that before you take that test. I would say do it as soon as it's available or first thing tomorrow. Everybody on the same page with that one? All right, so now that we've covered these issues about latent heat and calorimetry and bomb calorimeters and stuff like that, obviously every change of state requires a different latent heat. So for instance, when you sweat on a hot day, the sweat comes out as mostly water with some salt and some other chemicals that it's dispersing through your body. For instance, if you recently ate garlic or fish, that some molecules of those smells will certainly be in that sweat that gets on your body. But then what ultimately cools you is basically when that water goes from a liquid state, that sweat goes from a liquid state to a vapor state, which is evaporating, then it takes some heat to break those bonds between adjacent molecules and atoms so that they can go into the vapor state. That heat comes straight from your body and therefore cools your body down. So you need to know the latent heat of evaporation, and your book talks about that. For example, it's 2,450 kilojoules per kilogram for the vaporization, and compared to 2,260 for normal boiling. Okay, so it talks about that. That's some of the stuff you need to know. That's evaporation. Then we get into the kinetic theory of latent heats. In other words, is there some way we can figure out what those latent heats are by modeling the atoms as if they're little billiard balls that conserve kinetic energy, stuff like that. And then we get into the first law of thermodynamics, which I'll go ahead and give you now. The first law of thermodynamics basically says that the internal energy, so this is the first law of thermodynamics, says that the change in internal energy is equal to the heat added minus the work done by the system. So I need to expressly write down what this is. This is heat added to the system, and this is work done by the system. Okay, now you might be used to seeing Q plus W. That's what they normally do in chemistry, and that's because in chemistry they usually use the work done on the system. This is the work done by the system. So for instance, if the system is a gas and it's inside of a cylinder, if the gas expands, it pushes the piston up. It's doing work. That's a positive amount of work done. Therefore, you're going to subtract it because some of that energy went into doing that work as opposed to changing the internal energy or adding heat to the system. And then, of course, the heat added, it just means like doing what would cause the temperature to go up. So if you just think of E internal as being directly related to temperature, even though it's a little more complicated than the ideal monatomic gas we talked about, then it makes perfect sense. Hey, If I add heat, that's going to increase the temperature, which is consistent with that first law of thermodynamics. Not only that, if the gas expands, that's going to be at a loss of temperature. So that's why you have the minus there, and that should make sense. Now, in general, if you really, really want to see it, it turns out this is all really just conservation of energy. That's what the first law of thermodynamics is. So you could, I don't know why I did that extra little hiccup in my Y there. So you could, in principle, say that delta kinetic energy plus delta potential energy plus delta E internal is equal to Q minus W. And that's sort of a more full version of the first law of thermodynamics. Okay. So that's where we'll start next time. Time is up now. You're free to go. This video will be posted as soon as it renders, and I'll hopefully have you made your lockdown browser quiz by then as well. So everybody have a good evening. Make sure you just do that practice test as many times as you can. That's way more important than the individual homeworks in terms of preparing for a test grade. So do that, ask questions, get help, use Chegg if you need to, text me if you need to, contact other students if you need to, whatever you need to do. And then good luck on your test Wednesday. I will not see you until afterwards. We'll have a regular class, but you're done with lab once you finish your test. But we're going to finish chapter 19 after you're finished with your test in class. So have a good one. Good luck. I hope you all make a really high A on this first test. And I'm going to wait around for the last person to leave in case anybody has any questions. I know Bohan had some about homework.
Professor Younger, I
Yes.
also have a question about the one of our assignment is physics primer. Is that something we already did 241?
Yeah, you did do that same assignment in 241. It's extra credit this time too, though. So for instance, I tell you guys, I think what the syllabus says is I'm going to drop your 2 lowest homework grades. Now it's going to be your 4 lowest at least.
Okay, so this can conserve some extra credit. Okay.
Yeah, that one and the intro to mastering. Tanner raised their hand. What's up, Tanner?
I just wanted to confirm that the test we do still have to show up to like the TCC lab like in person.
Yes, that's a face-to-face test where you're using Canvas and the online multiple choice answering system, but you'll have the lockdown browser, so the instructor hasn't got to mind your computer monitor 24/7 during the whole test.
Okay, and
Don't
then
get caught with any internet capable devices. That would be bad.
okay, and then you said, I know we talked about it earlier, but in terms of like any formula sheets go, we have to make those ourselves, and they have to be like numbered, like according to the textbook.
Yeah, you don't have to number them on your sheet. It's just they're only eligible if they are numbered. Like I'm looking right now at the first law of thermodynamics, and it says delta E internal equals Q minus W. And off to the right, there's a parenthesis that says 19-5 and then a closed parenthesis. That 19-5 tells me that equation is one you can put on your equation sheet.
Okay, and no words accompanying it, right?
You can have a single word representing what the variable means, but I don't want any titles, any multiple words. Like I wouldn't want you to have delta E internal equals Q minus W and right next to it say first law of thermodynamics. That's blatant making use of something that we could actually ask you as a really easy question. What is the first law of thermodynamics? If you had it written on your equation sheet, that's sort of not helpful.
Okay. Alrighty. Thank you.
No problem. You're welcome. Anybody else have any questions?
I had a question about the homework problem you were reviewing before class.
Yes.
I could not figure this out for the life of me, and it was the
Nitrogen oxide schools one.
Yeah, the part B, and it was asking for the RMS velocity. So,
So remember, root mean square means root, or RMS means root mean square. So
right.
what you're wanting to do is take the mean of the square and then take the square root of that.
And we're taking the square of the median points.
Exactly. Like the first bar is 0 to 200. The
Mm.
midpoint on that one's 100.
Okay.
And I think we found it was 6%.
Yeah. Yeah.
So you take
6%. And then
0.06 times
oh, wait.
100 squared.
Oh, so you do 100 squared times point zero. Okay, that's what I was doing wrong. I wasn't multiplying by the percentage. I was just doing the median points squared and then adding them all up and then taking the square root, which wasn't giving me the right answer.
Right. Now, what you're supposed to do is when you finish adding all those products together, you're supposed to then divide that answer by the sum of the percentages.
Which is
But
just
you'll
one.
see that they add up to give you 1, so you don't have to in part A or part B.
I got that. Okay.
But you do have to take a square root of the answer when you're done, because that's the root
Mhm.
mean square. Otherwise, you're getting the average of the square.
Right. That makes so much more sense because I just kept like circling and the instructions on the problem were like impossible to follow. I was just like, God, I just need
Use
Younger to
those
just say it.
hints. The hints actually give you more details, so that'll help you. So feel free to use those on occasion. I thought I set it up where they wouldn't take off points for hints.
I don't think they do.
You think they do?
I don't think they do because I've requested a couple answers on hints, so I hope not because
Yeah.
they can be very useful.
Absolutely.
All
And
right.
that also is, one of the few chances you get to calculate a weighted average. So that's a good thing too.
All right. Thank you for that.
You're welcome.
Have a good night.
You too. Anyone else have anything? Okay, I'm not sharing my screen anymore. I should have done that a long time ago, but here we are. I'm back in my course and I'm trying to open up my lab and mastering. Does anybody else have any questions about any material?
Yeah, I think he left.
Yes.
It's just me here.
It's just you, Bahar? Gotcha.
Yes.
You're still asking about that numbers 7?
Yeah, the number 7 part B. So I get the part A right, but I just kind of a little bit confused on the part B.
It is chapter 18 homework, right?
Yes.
Okay, I'm pulling that up now. It seems to be working a little faster, so hopefully I can get there quicker. Yeah, it's coming up a lot quicker now. So it says answer statistics on this page are updated periodically, blah, blah, blah. That's not for you. Calculate the RMS speed of a nitrogen molecule at T. Determine how many times per second it would move back and forth across a D meter long room on average, assuming it made very few collisions with other molecules. So you were able to get part A.
Right.
It says calculate the root mean square speed of nitrogen. Determine how many times per second it would move back and forth across the 4.7 meter long room on average. So once you get the root mean square velocity, you're supposed to be able to take a measure of the relative velocities of the other particles, assuming you're bouncing with them, and you should be able to just divide the distance by the velocity. And the distance would be, of course, twice the width of the room.
Yeah.
So 0.7 times 2. So if you take that and divide it by the velocity, that should give you the time between collisions. If you want to know, or excuse me, that should give you, the time between collisions. And if you want to know how many collisions per second, then you flip it over. You take the.
Yeah, I saw the same thing. You just use those distance, whatever the distance they give to you times 2, because they add back forth, and then use those distance divided by your RMS. That's what I saw, but actually but I get it wrong on my answer. So I did a search online. There's a right answer side should use the V equals VRMS divided by square root of 3. So I don't know why we had to divide it by square root 3 here to get
Right. That is it. But that's if I remember correctly, that square root of 3 on the bottom is you taking into account the fact that the other particles are moving. If you remember in your reading, at one point he says a more correct, this is in the very last section where he talked about mean free path. He said a more accurate analysis is obtained by calculating what the speed is relative to the existing molecules. And if I remember correctly, that's a correction of 1 over the square root of 3. So I think that's where that came from.
Okay, so this is this is some formula to use when it comes to like the molecule.
Right.
So your V, you had to use your V equals VRMS divided by square root of 3.
Right.
Okay, yeah, I saw this formula, but I just don't know where it come from.
Yeah, I think that's what it is, but I could be misremembering. For some reason, I thought it was the square root of 3. It could have been the square root of 2. But yeah, if you look in chapter 18,
yeah, it is. So when you put, I want to do that, apply that formula square root 3, then I get the answer 3. But I just don't know where this square root 3 come from.
and you're not expected to. It's way beyond the level of this course, but it's in that it's an 18.7 mean free path, if I remember correctly.
Yeah, I think that makes sense now. But
yeah, it's so yeah, don't, and I wouldn't worry too much about not knowing that, because clearly that's they didn't even give us that part, because it's kind of a beyond the scope of this course. So I wouldn't worry too much about just not knowing that little part.
Okay.
Right.
Thank you for answering me, Professor Younger.
No problem. Have a good one, Bohan. If I find out anything else, I was still looking for it. I still ain't found where it said the square root of 3. But anyways, I'll keep looking for it, and you can too. But let me know if there's anything else I can do to help you.
Okay, thank you, Miss Younger. You have a nice evening.
You too. See you, Bohan.
Bye bye.